Okay, so good morning, everyone. I just wanted to show you a simple example of what Filomena has been explaining a few minutes ago. Fresco, when you go to the manual of Fresco, you will see that it has many possibilities. You can fit, as Filomena said, many types of observables, parameters, and so on. But I think that we will be happy if we all manage to make a simple fit of some data set of the type of data that you were analyzing yesterday. So some elastic data, some angular distribution that you or someone else has measured, and you want to compare this with some optical model calculation. So yesterday some of you were worried because when you pick some data from some database and then compared with some global prescription, the agreement was reasonable but not perfect. So there is nothing to worry about that, because typically the situation is even worse. But some of you got quite good fits of the data, but sometimes we want to improve this fit of the data. So this is one of the situations in which we would like to use Fresco to get an improved fit of the data, and of course after that to interpret the new parameters. It's not just to get a curve that goes through the data points, but to get some interpretation of these new parameters. So I give you a very simple case that is an optical model fit. So this is just borrowed from Filomena's slides. So the idea is to minimize this quantity, this chi-square quantity that is measured as the difference between our theoretical prediction for each point with respect to the experimental result, and it is weighted by this inverse of the errors. So data points with larger errors, of course, will have a smaller weight on the chi-square, as you all know. So I go directly to our example. So our example, imagine that someone has measured lithium-8 or lead. Lithium-8 is an unstable nucleus, and you want to get an optical model fit of this lithium-8 lead data, 33 MeV. So the idea is to minimize this chi-square. So we need, to use Fresco, essentially we need 3 files. So the Fresco input itself, the kind of input that you were generating yesterday. Then Fresco, I don't know if Filomena mentioned that, uses a subroutine from CERN that is called Minuit. You mentioned that, sorry. So we need this the input for this subroutine, for this Minuit subroutine, and then we need an additional file that I call search.in that contains the information on the parameters that we want to adjust, the data points that we want to fit, and so on. So we will run the main input, this Fresco, that will call this search.in to look for this information, and it will run automatically our input as many times as needed in order to get a minimum of the chi-square. Okay, so this will be done automatically. We just have to run this sfresco.in with and the executable is called sfresco actually. So it must be already installed our Talent server. So you can play with it this afternoon. And I think that Jeff has uploaded also this particular example, so you don't need to start from zero. You can use this as a starting point for your homework today. Okay? So imagine that these are data. These are actually these are some real data from lithium-8 on lead. So these are the data points, and you say, okay, I don't have an optical potential for lithium-8, but I have an optical potential for lithium-7 on lead that should be similar to lithium-8. It's just 1 neutron less than lithium-8. So this could be a first attempt. So the red line here is the calculation, the optical model calculation for elastic scattering of this system at 33 MeV or 34 MeV. And as you can see, the agreement with the data is not wonderful. It's not as good as we would like. But
have
yeah.
you adjusted the radius?
Sorry?
Have you adjusted the radius?
Yes, the only thing that we have used here is to use the same reduced parameters, but this reduced parameter is then scaled by the masses, so 8 to 1/3 plus 208 to 1/3. So in some sense, we are taking into account the fact that the lithium-8 must be a bit larger than lithium-7. From a very naive point of view, without taking into account any details on the binding and so on. So just thinking on the number of nucleons that we have in lithium-8. So that is the reason why it is useful to use this reduced radius that you don't like at all, I guess, after all the confusion that it generated yesterday. But this quantity is in principle more stable when we compare many nuclei, different masses. It has a value between 1.1, 1.3, let's say. But of course, the absolute radius will change according to the mass. So that is the physical reason of using this reduced radius. So this is the input example. So this is the kind of input that you generated yesterday for the other cases that Filomena suggested for the homework. So this is our input sample, and I believe that now all of you are able to generate this by yourself. But anyway, it's in the Talent website, so you can download and play with it. And the key part here is the optical potential. So remember, we have to define optical potential for the lithium-8 lead. So this is the potential CPOT number 1. So potential number 1 is here. And these are the parameters that we took from literature for lithium-7. So it's for a different system. Energy is 34.4. So we have also put the correct energy. So this is our starting point. So we have already our Fresco input. Now the Minuit input, it contains many possibilities, many parameters, but I don't think it is worth to explain all of them here. So I just tell you that most of the time you can just leave all these parameters, use the default values that you find in the manual. You don't have to worry about the meaning of this, but if you are curious, you can go to the Fresco manual or to the Minuit manual, because these parameters are actually for Minuit. So there are many possibilities to fine-tune the fit. So I just highlight here the first line, search.in, that is the file name that we will use to specify our parameters. So in principle, you can use this as in the example that we will provide you, and you don't have to worry anymore about this. Maybe just you want to change this name here, you want to have different calculations. Okay, so this is an important file. This is the search.in input, where we specified what variables will be adjusted. So in this case, well, now we will go part by part. But after we have generated this, then we run sfresco with a command like this, and we will see the result. So the first line in this search.in contains just the Fresco input. So Minuit will run this, will call Fresco, and Fresco will run this input, and we'll change the parameters, trying to find some minimum in the chi-square. So this is the input, this is the output. These two corresponds to the number of variables that we want to adjust. And remember what Filomena said, don't be too ambitious. First time, don't try to say, okay, I have 6 parameters, so I vary all of them, and maybe you will get a perfect fit, but with parameters that have no physical meaning at all. So you have to try to keep the physics under control. So it's better if you start just by fitting some physical grounds, thinking, okay, maybe this system, the potential depth will be slightly different, the potential can be deeper. So try to think on the physics and try to figure out what are the parameters that are more sensible to change, to vary. So I decided here to vary the potential depths and to fix the radii. So I have two variables. So this name list, again, this uses the name list style. So this is, we have to add one of these name lists for each variable that we want to adjust. So here, the kind equal 1 corresponds to specifies the type of variable. Of course, we can vary potential parameters. In this case, this is what makes sense. But if we are doing, for example, a transfer calculation, maybe we want to adjust some spectroscopic factor. So this will be a different kind of parameter. So if you go to the manual, you will have a list of all possible parameters that can be adjusted. So type equal 1 corresponds to a potential parameter. Kp refers to the index of the potential in the input. You may think that in our input there is a single potential, but in general we can have an arbitrary number of potentials. So this is to specify what potential we want to modify. This then P line, remember that each potential contains in general several components, the Coulomb part. Then we can define a second line for the volume nuclear part. Then some of you yesterday had to include some surface 10. So this is included with an additional component, the spin orbit part. So this, in the same order that is included in the input, this is the index that identifies a given component of the potential. So in our case, let's go back to our potential. So we have two components. The first one is the Coulomb potential. The second one is our nuclear potentials. That is the one that we want to modify. The Coulomb potential, of course, is well defined here, so we don't have to modify it. So in our case, we want to modify the second component. So that is why we have P line, potential line equal 2. Then col stands for column. So column 1 corresponds to the variable. So you have in general for each potential 6 parameters, 6 variables, P1 to P6. So column 1 corresponds to the variable P1. And P1, remember, is the depth of the real part of the potential. And for the imaginary part, we have 3 parameters, P4, 5, and 6. So 4 is the depth of the potential. That is why in the second line we have 4. I didn't say that the name is just the name that you want to give to this parameter to identify it more easily in the output. Just the name you want to give it. And this is also important. Many times for physical grounds or physical reasons, you want to constrain, because Esfresco knows nothing about physics that we are studying. So maybe it will get a perfect fit, but with a potential that makes no sense. Maybe using a radius that is 14 Fermi, it doesn't make any sense. So of course, so this is a way of constraining the physics. So it's also a way of avoiding some local minima that makes sense only numerically, but not physically. Okay? So I was not very ambitious here, and I chose a broad range of parameters. Okay, the next section is the data. So we have first to specify the kind of data that we are going to fit. So in our case, the type corresponds to the observable that we are going to fit. It could be, for example, a cross-section with respect to the energy. So excitation function could be some transfer, could be some elastic data. So the type equals 0 corresponds to angular distribution for a fixed energy. That is what we want to fit. We have an elastic angular distribution for a fixed incident energy. So this is type equals 0. The I scale corresponds to the units. So I scale equals 2 is milliband per stereo-radian. That is the usual choice. And ID corresponds to the way in which the data is specified. For example, in elastic data, we can specify the data in absolute units or divide by Rutherford. This is, again, important. So in this case, you, you remember the plot, we have some ratio to Rutherford. So this corresponds to corresponds to ID equal 1, that is a ratio to the Rutherford cross-section.
Do you want to say how much it is for the absolute? Because many of the data are going to be an absolute.
How much, sorry?
Do you want to say what that variable is for the absolute cross-section?
I don't remember. Do you remember?
It's 0, isn't it?
It's 0? I have to check the manual, I don't remember. And then absolute error, again, so after this line we will give some the data. So this is the angle. There are of course more points here that I have skipped. This is the cross section relative to Rutherford, and this corresponds to the error bar. So we have to specify also if the error bar is a relative error. That is relative, it's not a percentage, it's relative to 1. Or it's an absolute error. So in this case, it's an absolute error. So these are the main variables. There are some others that you can see in the manual, and then we will check what is the value of the variable for the absolute, because I am not sure now. So this is part of the output that you get once you run this the sFresco. So I just selected some pieces. The output is longer than that, but so at the beginning you get the original values of the variables that you are going to fit. So make sure that Fresco has identified correctly the variables and you didn't make any mistake with a column or component and so on. That is very easy to make mistakes. So Fresco will give us, sFresco will give us the initial chi-squared. You see, ideally should be less than 1. This is a perfect fit, and we are starting with almost 80, so it's a poor fit to the data. So, but this is before doing any adjustment of the parameters. Then these dots, this period correspond to all the steps. So sFresco will run many times Fresco with by changing the 2 parameters and trying to find this minimum of the chi-square. So hopefully after this search we will get a better chi-square, a better adjustment, and this is the end of the output. So let's look at first this part. So these are the final values of the parameters. So the V changing from 15 to 12, and the W, the depth, from 13 to 60. So this probably means something, I mean physically, apart from numerically. So essentially the real part remained almost the same, but we have a large increase of the imaginary part. So this is telling us something, we should be able to interpret this in terms of physics. But before that, so let us look at the chi-square. So we started in 80, now we are 1.4, so this is a pretty reasonable fit, so we should be happy with that. And you have the contribution also to the chi-square of each point. Sometimes it might happen, for example, here there is a point that is ruining, that is deteriorating our fit. So sometimes it's because this data point in particular doesn't make any sense. So maybe one is tempted to remove this data point if one has a good reason to do that, not just because we want to have a chi-square less than 1. But sometimes this is there are reasons to believe that some data in particular, some point is not reasonable. So it's useful to see what is the main source of our chi-square. What are the points that are weighting more? And this is the correlation matrix that Filomena was also mentioning, that give us an idea of the dependence of the different parameters in this chi-square fit. So ideally, if we have completely independent parameters, this should be a diagonal matrix with 1 and 1. You see that the non-diagonal terms here are 0.6. So this indicates that we have some correlation. So this means that, for example, if we decide to fix, for example, the real part, then we can possibly get an almost as good fit, but with some maybe different value of the imaginary part. So you will have a range of parameters for the real and imaginary part, so you will have some ambiguity in the final parameters. Okay. Okay, so let's look at the final. So this is, so then we have to modify our input with the final parameters that we have seen. Actually, this is not necessarily because Sfresco will generate even the plot for us, but I think, well, I prefer to do it by hand. So this is the modified input in which we just changed this potential depth to the values that has been found by Sfresco, right? And this is the fit. Not a so the black line is the result of this adjustment. So it's not a perfect fit, but we don't want in general to have a perfect fit. So the important thing here is that what the new parameters are telling us. So this is also part of the task of the interpretation of the data. So in this case, well, we are not going to enter into details, but lithium-8 is a more weakly bound than lithium-7. So there is more chance to occur processes in which the system dissociates. So every process that removes flux from the elastic scattering will contribute, to this imaginary part. So this is indicating that for lithium-8 we have more chances to have non-elastic processes, and this is actually the case. So the optical model by itself doesn't tell us what are these processes. It could be transfer, could be breakup, so we don't know. So this is what we can say just from the optical model, but it is giving us a first indication that there are processes going on. So probably then we have to combine this with a more sophisticated analysis, coupled channels that we will see tomorrow, or we have to go to the spectra and to ask our colleagues, experimental colleagues, to see, can you tell me what observables, what events do you see in your spectra? Do you see, for example, indications of transfer or breakup, whatever? So this is part of the feedback that the theorists have to do with the experimentalist. And then we go back to our Fresco input, and we can improve our theory and continue this feedback. So I think that this should be enough. So this has been shown already by Filomena, so I don't think I have to give it again. So we stop here, we have a coffee, we wake up. Okay.